your question about how elastic collisions can, avoid transformations to other types of energy is a good question. In reality, you know, collisions are not 100% elastic. Pretty much any collision in general will always lose some energy to something else. So this is an ideal situation that basically never happens, like if we're being very strict about it. But there are things that are very close to elastic, and there are things that are very, obviously inelastic.
Okay.
So, so I guess it's a bit like, when we talk about in chemistry ideal gases, which is actually defined by elastic collision. And no gas behaves 100% like an ideal gas, but many gases are very close to that, like close enough for our purposes.
Okay.
So, or for example, absolute zero is an ideal temperature of like zero Kelvin, right?
Yeah.
We can't reach that. Like it's impossible to reach that, at least with our current understanding of technology. But, we can get very close to that. And we can still have this idea of what 0 Kelvin would be, even if we can never actually get there.
Okay.
Does that make sense? So in practice, in real world, no collision is 100% elastic, but there are collisions that, would be, that for all intents and purposes, we can model as an elastic collision. And it will be pretty, like, the predictions will be pretty close to what we expect, or what we get. So can you think of any examples which might be considered an elastic collision? Like close to, anyway.
When two sponges collide each other?
Well, when two sponges collide, often they don't, they kind of just become squishy and then fall down, right?
Yes.
So do you conserve the kinetic energy?
Doesn't.
Often not, right?
Yeah, no.
Often if you had something fast running into a sponge, it's not fast enough to run into the sponge anymore.
Yeah.
So you lose a lot of the kinetic energy. So that's actually a very, that's a typical example of an inelastic collision, right?
Yes.
And so using an elastic collision is going to be very far from accurate in that situation there usually, depending on the sponge obviously and the objects, but in the ones we're thinking about, it's not, elastic will not be a good example. But an example of an elastic collision that's often used is like billiard balls. So when you're playing pool, right? So if you hit, your ball with your white ball, then often, if you hit it straight on, then for example, let's take a very simple example, right? You've probably seen this a few times. If you use the white ball called the cue ball to hit this ball straight on, then often you can get it so that this ball stays here and doesn't move, and the blue ball goes forward, right?
Yeah.
And so is the kinetic energy before and after very different?
Maybe not.
Maybe not, right? Because, if you assume that the masses are similar, and if you assume that the velocity it moves off is equal to or very close to the velocity that this was, then the kinetic energy hasn't changed much.
Yes.
And that would be an example of, what we would consider close enough to consider an elastic collision. That's one example.
Okay. Yeah.
Now, obviously, it's not 100% elastic strictly, but it's close enough to think of as elastic. Yeah.
Yeah.
So, for example, let's take a look at question 20. So it says, suppose the force acting on a tennis ball, mass 0.06 kilograms, points in the positive direction and is given by the graph shown. So you've got a graph that looks something like this. You have it in front of you, so I won't draw it fully out, but it looks something along the lines of this. right? Now, use graphical methods to estimate the total impulse on the ball. So how would we estimate the impulse here?
Sorry?
So the question asks you to estimate the impulse, right? Using graphical methods.
Yeah, yes.
So how do we estimate the impulse?
Like the area under the like under the curve.
Yep. So basically you just, you know, work out what you think the area under the curve is and you basically count it up.
Mm-hmm.
Do you are you comfortable doing that or?
Like just go through it maybe.
All right. So you've got, it might be easier if I So we essentially counted up the squares, then we said that the impulse is therefore approximately 1.1 kilogram meters per second, right?
Yep.
And then the next question then asks for the velocity of the ball after being struck. Assuming that the ball is being served, so it's velocity of the ball after being struck, assuming the ball is being served, so it's nearly, okay, so basically we're saying that the ball at the start was at rest.
Mm-hmm.
And we know that the mass is 0.06. Does that make sense?
Yeah.
So the momentum before is basically 0, right?
Mm-hmm.
Now, you had this event. What's this event? What happened in between?
Sorry?
So you had this event, right?
Yeah.
So what's in between? What happened in between? The start and what happened?
Collision.
Well, you can think of it as a collision, but essentially you hit the ball, right? You applied force to the ball.
Yes.
And you can think of that as a collision if you like, but you know, you applied force, and then after, that means you've now got momentum, right? It's now moving.
Yeah.
We don't know what the velocity is. We know what the mass is. Now, do we know what the momentum is after?
Well, I mean, we know the impulse. So
Correct. Exactly. So unlike a collision or explosion, where the momentum is conserved, here momentum is not conserved because you applied force over a period of time.
Yeah.
And so you applied force, and as you correctly indicated, this is the impulse, which represents the change in momentum, of course. So that means we now know, having applied this impulse, which we've now estimated, that the momentum is about 1.1. Mm-hmm.
Yeah.
And if we know that, then we can calculate V. Because if the momentum is around 1.1 and M is 0.06, then V is about 1.1 divided by 0.06, which will be about, you know, so 55 over 3 meters per second, and is around, that's weird, okay, which will end up being 66 kilometers per hour. Now, they didn't ask you to convert that, but I'm just converting that to give you an idea if that functions better.
Mm-hmm.
Does that make sense?
Cool. Yeah.
Good. And so that's how you do that impulse question.
Okay.
All right. So let's see if we can just pick another sort of impulse question that, all right, so let's do, for example, question 19. question 19 states a 95 kilogram fullback is running at 4 meters per second to the east, let's call that to the right, and is stopped in 0.75 seconds. So it took 0.75 seconds by head-on tackle by a tackler running due west. So someone was running west and they stopped. Does that make sense?
Mm-hmm.
So A, calculate the original momentum of the fullback. You know how to do that, right?
Uh-huh.
Well, how do you do that?
Well, mass times E.
Mass times?
Velocity.
Yeah. So therefore, it would just be 95 times 4, which would be 380 kilogram meters per second. Okay. Now B, because, you know, he had this momentum, but later he stopped, right? So what's the momentum after? Remember, he stopped.
Okay, so should be 0.
Right. So what's the impulse?
Um, 280
Yep. Direction?
east.
Well, it was east. Now it's 0. So what was the change?
Oh, so should be west.
Or you can think of it as negative 380 east, which means it's 380 west, right?
Mm-hmm.
So the impulse exerted on the tackler. So what's the impulse on the tackler? So the tackler stopped this person, but remember, it's essentially a collision, right?
Yes.
So the impulse on the tackler must be opposite to the impulse on the fullback. So that's 380 kilogram meters per second east.
Oh.
And D asks you to calculate the average force exerted on the tackler, or you just need to recognize that impulse is equal to force times time.
Yeah, so divide by time.
We know impulse is 380. We don't know the force, but we know the force. The time is 0.75. So it's just 507 newtons approximately. And that's how you do that question.
Okay. Yeah.
Does it all make